Swayam Prabha. Digital India. Educated India.
I will see some cryptographic applications of the basic number theory we have been talking about so far. But before that, I want to start with a discussion on computational efficiency. So, if you consider a binary number, written binary digits 0 and 1, you can have very huge numbers which have very short representation. So for instance, consider a 256-bit integer. 256 bits is very little data, right? And a number, the largest number that you can fit in there is 111, the 256 ones. That's the integer 2 to the 256 minus 1. How big is this number? So can you just write a little computer program that counts all the way from 0, 1, 2, 3 up to this number 2 to the 256 minus 1? Okay. And the short answer is actually no. And not even if you had a very, very fast computer that ran at the frequency of molecular vibration. So it's a frequency at which atoms vibrate inside a molecule, and that's something like 10 to the 14 hertz. And further, suppose your computer runs for a very, very long time. In fact, suppose it runs for the entire estimated lifetime of the universe so far, and that's at most 10 to the 18 seconds. So that's a lot of time. And even so, so this gives you, you can count up to something like 10 to the 32, and that's well below 2 to the 256. So you won't be able to count all the way to 2 to the 256. How about, if you're a computer scientist, you might say, okay, it's not all about clock rate. You should probably have multiple processors, you should have many cores. So you should do this counting, you should distribute this counting across several processes. Okay, so suppose I let you recruit every atom in the Earth to do this counting task for you. Okay, so there are 10 to the 50 atoms. And now, if you could actually do this, you would just about be able to do this counting, because this gives you 10 to the 82, you can count up to 10 to the 82, which is quite a bit more than 2 to the 256, okay? But still, that's something that will fit into a 272-bit integer. And in fact, even if you recruited every elementary particle in the universe, in the known universe, and that's estimated to be at most 10 to the 80, that'll give you, you can count up to 10 to the 112, and that's still only letting you count a 372-bit integer at most, okay? So put another way, the whole known universe cannot count, and here counting just means molecular vibrations. It cannot still count up to a 400-bit number, okay? So it's completely hopeless to try and build a computer that just simply goes through all the numbers in the range, all 400-bit integers. On the other hand, so it's looks like these numbers are humongous numbers. You probably can't do anything with that. Well, that's not quite true. On the other hand, you can quickly do computation on them. You can add, multiply, divide much larger numbers, numbers which are thousands of bits long. Even find GCD for them, okay? And here the algorithms are pretty simple. They're addition, multiplication, and division are all the high school algorithms for those tasks. Exponentiation is you should do using repeated squaring, and GCD you can use Euclid's algorithm. Okay? So pretty simple algorithms, and that'll let you compute on this really humongous numbers very quickly. In fact, all these algorithms run in about n step, or at most n square steps, where n is the number of bits used to represent your number. Okay, and say 400 square steps is nothing. It's pretty short. It's something your computer can do very quickly. So the key thing is to use these algorithms which take time proportional to the number of digits in your number, and not the actual number itself, right? You cannot even count. So if you try division by repeated subtraction, or if you tried exponentiation by repeated multiplication, then yeah, there is no hope of completing x to the y, where y is a 400-bit integer, right? But if it's something you're doing using repeated squaring, you'll be able to do it quickly. This, say, assuming you're working modulo some numbers so that all your results also fit into 400 bits. So there are certain things you can do very efficiently with these huge numbers. On the other hand, there are certain problems for which we don't know something much faster than counting, or it could be much faster than counting, but it's still really, really slow. So say you have an algorithm that takes 2 to the n by 2 steps to do some computation on n-bit integers. That's much faster than counting, but it's still really, really hopeless. If my n is 800, we are still talking about 2 to the 400 steps, right? And so, these are problems for which we currently do not know any algorithms, but in fact, for many of these problems, we believe no such algorithms exist. So it's not just a matter of, somebody being clever enough and finding this algorithm tomorrow. It's actually that, it's conceivable that these problems simply do not have efficient algorithms, and there's probably no better way to do those computations than take something in this order. Okay. Unfortunately, as of today, we don't know for sure. It's only a belief based on failure to discover better algorithms. But this is probably more a function of the fact that we don't know how to prove such algorithms do not exist, even though such algorithms may not actually exist, right? So it's a limitation of the current mathematics to prove the non-existence of algorithms. And so widely, the non-existence is believed to be true. Okay, so this kind of computational hardness, that certain problems are very difficult, or at least we believe they are very difficult, forms the basis of much of modern cryptography, including public key encryption and other things that you use routinely. Okay, so that's what I wanted to talk about today. So a couple of examples of using modular, this kind of hard problems in modular arithmetic for the purpose of cryptography. Now, when I say for the purpose of cryptography, there are several things you would do in cryptography, and we really are not going to formally define any of this. Instead, I'll just jump into a particular cryptographic primitive, something called a trapdoor one-way permutation, for which we will use these number theoretic operations. So what is a trapdoor one-way permutation? So it's a mouthful. So it's a permutation which has some properties, right? So what is a so first of all, there's what do you care? Why do you care about these things? These are the kind of objects that are used in building more immediately useful applications like public key encryption. Okay, so what is this? So it's a permutation. So what that means, it's a bijection. say it maps 400-bit integers to 400-bit integers such that no two integers are mapped to the same integer. So it's a one-to-one function from the domain of, say, 400-bit integers to 400-bit integers. So that's what a bijection is. And it should be easy to compute to be able to use it in something like an encryption algorithm. It's a function that's easy to compute, but it's one of these functions which we believe is hard to invert. Okay, so since it's a bijection, there is an inverse function that's well defined, but that function should be hard to compute. Okay, so that's what's called a one-way function. And finally, even though it's hard to invert, if you knew a certain secret about this function that you can find while setting up this function, if you knew that secret, that will make it easy to invert as well. Okay, and that secret is called the trapdoor. So that's what a trapdoor one-way permutation is. It's a permutation that's easy to compute but hard to invert. However, it becomes easy to invert also if you know the trapdoor. We'll see two candidates for trapdoor one-way permutations, and these are both based on modular exponentiation. They're called Rabin's function and the Rsa function after their inventors. And I say candidates because they are indeed permutations that allow efficient inversion when you have a trapdoor. However, we do not know how to prove that they are hard to invert. So this is a conjecture that they are one-way functions. Okay, so that's where they are candidates for trapdoor one-way permutation. Both of these are based on modular exponentiation, where the modulus is of the form p times q for two large distinct primes p and q. And it's important that we are using a composite modulus and not a prime modulus, because instead if you use the prime modulus, both these functions would become easy to invert. In fact, not just that, even when you're using composite modulus, if the prime factors of those modulus are known, that would make it easy to invert. And this is by using the Chinese remainder theorem, or the CRT representation of these of numbers modulo m. So this, in fact, also tells you that here is a trapdoor. If you know this factorization, that would serve as a trapdoor for inverting this function. Okay. All right. So what are these two functions? So first, let me start with Rabin's function. So this is based on finding square roots. So we talked about, in ZP star, where P is a prime, every integer has exactly, every element in ZP star has exactly two prime factors for P larger than 2. And however, if you restrict yourself to the quadratic residues, then squaring becomes a permutation, provided p minus 1 over 2 is odd. Okay, so this is an example of such a case. So where minus 1 is not a quadratic residue, for such p, it's a permutation. And in that case, the because the permutation is easy to compute in the forward direction, it's just squaring, but it's also easy to invert. Okay, and we saw this, that the inversion is just obtained by modular exponentiation, and this we can easily verify this z in QRP star, where of the form x square, then you can plug in, you can check what is the square of this thing, and you would get back z, right? So the square of this will be equal to x squared, and that's equal to z. And this just used Euler's torsion theorem, or Fermat's little theorem. Okay, so this cannot by itself be a candidate for a one-way permutation. And as I mentioned, what the Riemann function does is that instead of using QRP star, it would work with QRM star, where M is a product of two primes. So yeah, so that's a function. It's simply the function is simply squaring modulo M, and it's where M is a product of two primes, very large primes, say thousands of bits long. And we needed these primes to be such, so it's not always a permutation. We needed some properties, namely p minus 1 over 2 and q minus 1 over 2. You needed them to be odd for, for squaring to be a permutation in QRP star and QRQ star respectively, and therefore in QRM star by Chinese remainder theorem. So this condition p minus 1 over 2 is odd and q minus 1 over 2 is odd. You could equivalently write that as saying p minus 1 and q minus 1, they're even numbers, but they're not multiples of 4. So they leave a remainder 2 when you divide by 4. Okay, so so if p and q are 3 modulo 4, then this function is a permutation. This, as I mentioned, follows from CRT, and the fact that this function is a permutation modulo in QRP star and in QRQ star. And also, it has a trapdoor for inverting, namely the factorization. Again, this is by using the Chinese remainder theorem. Okay, so it is a permutation and it has a trapdoor. Those are facts. And okay, by the way, this is the inversion algorithm explicitly written out. You take your number, you find its Chinese remainder representation, you take the square root in that Chinese remainder representation using what you know for prime moduli, right? So these are both modulo P and modulo Q. And then you can go back to modulo M using extension. Okay, so so it's a fact that's permutation, and it has a trapdoor to invert. What is a conjecture is that it's hard to invert. If I just told you M, where M was constructed in this way, and if I did not tell you P and Q, then it's hard for you to find the square roots. Okay, all right. So that's Rabin's function. Rsa function, named after Rivers, Shamir, and Edelman, looks very similar. It's also a modular exponentiation, but the exponent is not 2. It's some integer e. Again, you have M as before, product of two primes. But in this case, the requirement on E is that it's actually co-prime with phi of M. So phi of M is p minus 1 times q minus 1. And you want E to be co-prime with p minus 1 and with q minus 1. So one choice of E is to just take E to be 3, so that this computation is pretty quick, right? You don't have to do a lot of repeated squarings. You just do squaring once and then multiply it with x. So x cube is easy to compute. However, in this case, you have to take p and q so that this property holds, right? P minus 1 and q minus 1 should not have 3 as a prime factor. In this case, I claim that it's actually a permutation in Zn. In fact, it's how do you see it's a permutation? If I show you an inversion, a function that inverts this function, then it should be 1-to-1. Otherwise, it won't be possible to invert. And I claim that that inversion is actually just another Rsa function with a slightly different modulus. So instead of, sorry, same modulus, slightly different exponent. Instead of D, instead of E, you have exponent D, where D is actually the multiplicative inverse of E modulo phi m. So we'll see that in a second. But if that's the case, then that makes it a trapdoor permutation, because you can use D as a trapdoor to carry out the inversion. Okay. So why is D, D, namely the multiplicative inverse of E, a trapdoor? Well, in Zm star, you can see that from directly applying Euler's torsion theorem. In fact, it's not just that x to the ed is x. In fact, x to the ed minus 1 is 1 in Zm star. But also, as we saw last time, when m is a product of distinct primes, the fact that x to the ed is x when ed is 1 modulo phi m, that extends to this composite modulus, not just the prime moduli, and this follows from CRT. Okay, so it is again a fact that there's a permutation and there is a trapdoor. What is a conjecture is that it's a one-way function. Okay. So that makes it another example of a candidate trapdoor one-way permutation. So Rabin function and Rsa function are both candidates. You might, just one word on Rsa, you might encounter Rsa as an example of an encryption scheme. Well, that's not strictly speaking, this function here is only a trapdoor one-way permutation candidate. To use it as an encryption algorithm, you need a little more, some randomness to go along with this. But you would still come across Rsa function being referred to as an encryption algorithm, or sometimes called the textbook Rsa encryption algorithm. And it's not an encryption algorithm by itself. To make it an actual encryption algorithm, you also need some randomness.